Too. All right, our next keynote dives into the emerging solution of ZDAs, Zero Trust Distributed Applications. So the concept of zero trust is a major paradigm shift in cybersecurity. It throws out the old idea of a secure network perimeter and embraces the philosophy, never trust, always verify. This requires continuous authentication, least privilege access, and micro-segmentation for every single user and device, whether they're inside or outside the network. And when you apply this philosophy to decentralized systems, you get ZDAs, applications that extend cryptographic trust from the blockchain all the way through to the user interface and the business logic. And so our next speaker, Sam Hassan, will talk to us a bit about digital identity and the portability of that in the coming future.
Hey, everyone. So before we start, I wanted to to give an intro, a very quick intro about myself here. I come from a distributed system background. I'm leading the engineering team at Lightshift Capital. And before that, I worked at the core team at Chainlink Labs, where basically we collaborated with more than 30 protocols there in their first few days, and with the very early teams. And before that, I come from Google, where I worked at search infrastructure and Android operating system. So I'm here to introduce to you this novel idea, the novel research outcome that we produce at Lightshift. But before we get there, I think it makes sense to start from the beginning, start from where blockchains started, and as an industry, specifically from an engineering perspective, how long we came from the start. So the beginning is what I call the monolithic era. And this is a time in the blockchain space where all the computation and all of the data was basically in the same layer. This is like the Bitcoin, the Ethereum, and Solana, and the Cardano of the words, where most of the execution happened on this single layer. And when I say execution here, it's data computation, data availability, consensus, sequencing. Everything is in the same place. And you could easily see why we ran into a lot of problems with this. Transactions were very slow, applications were very expensive to run, and it seemed like it's very, very hard to go from there to competing with the incumbents in the Web2 space, whether it's the Visas or the MasterCards of the world on the financial sector, or if you think about it, the big social media networks, the big applications on the retail, like the P2C applications. So we came together as an industry, and we tried to attack this problem, make the blockchains faster, make them cheaper, and we tried everything to get there. So one of the ways is to move the computation on top of the chain, and this resulted into a whole class of roll-up L2s, the optimisms and arbitrums and Bayes of the word, and they gave a quite refreshed look at what a blockchain would look like. They're basically the first take on a modular blockchain, where the computation happens rolled up, and then basically gets consolidated on a settlement layer. In this case, it's Ethereum. With that also came a lot of problems, right? You have the sequencing problem, basically detaching the sequencing from the base layer, but you also have a limitation on this mechanism that basically locks users out of their funds and locks users out of their funds on the network for a very, very long time. So another way we attack this problem is let's move the computation to the side of the chain, and we call them sidechains or parachains. And the idea here was to off-chain, basically short computation for these applications into their own spaces. And it seemed like a very good idea, and again, it separated workloads, and it allowed applications to operate completely separately while still being connected by a main hub. This is the case for Polkadot, Cosmos, and early versions of Polygon. And this worked really well, but then we realized that with that model, we buy into kind of like owning, every application would own its own consensus, would own its own like validator network, and whether it's partially or completely, would also own its own security assumptions, meaning that the base layer or the settlement layer doesn't really cover the full security assumption of the upstream application. So that's the second direction, and then the third direction is that we wanted to shift everything to math. And this is, or the encompass in this piece are ZK Sync, StartNet, and Scroll, where the idea here is let's build everything off the chain. Let's prove everything on-chain. Let's do all the computation in a very expensive way off-chain once, and then have that computation integrity checked and proved on a settlement layer. And again, this is one of the frontier research that the blockchain industry contributed to, and it allowed us to grow as an industry in a lot of different directions. But again, it comes with a cost, whether it's like the high proof cost of the chain, whether it's like the trust assumptions that a lot of these blockchains did not nail yet from a cryptography perspective. And then we also have the problem with data availability, where we have to retain the data of the applications completely detached from the blockchain and only make it available to users so they can make proofs of their data. There's a lot of limitation that comes with that. And again, those are just like 3 examples of ways to kind of like increase the throughput of a blockchain, make it cheaper, make it faster. A lot of like novel approaches happen as well. Like if you look at Solana, Alpenglow, or with like the novel partially ordered or quasi-ordered blockchains, whether it's Pod Network or Delta, who are trying basically to, again, the aim here is make it faster, make it cheaper. And I think this brought us in a place where blockchains are very quick and very cheap. Now we can get that to the magic number of like 10,000 TPS, transactions per second, and we also can do transactions in under 1 cent. And somehow we still manage to push that limit when it comes to application users. If you look at like something like a Hyperliquid or most like high frequency DEXs, where they push through that limit very easily, or if you look at like any major launches that happen on chain, and you see that we're pushing that limit and we're pushing these numbers. And even though there is a lot of research out there on how to make it even faster and even cheaper, we decided to kind of like take a step back and try to think more, what are we measuring here? What are the things that matter when it comes to building applications in a decentralized way? And in a way, like, what's the T? And I remember we had a call where we kind of like, someone asked the question, what's the T in there? And we realized that the whole premise here is we want to build applications that derive integrity and derive the trustless assumptions from a blockchain, but they don't necessarily need to live 100% on the blockchain. And this is what kind of like brought the idea of building zero-disk applications, or ZDAs. ZDAs are applications that live in this hybrid world, where part of the computation happens on-chain, most of the computations happens off-chain, and data custody happens in a decentralized way, enabled by the blockchain. So the core components here are, basically there are 3 core components here. The first one is the blockchain itself. It's the main coordination hub for ZDAs. It's the place where applications coordinate the execution, but not necessarily run the computation itself. It's where the identity is derived, the universal identity across all of ZDAs are derived. And it's also where payments happen. So one of the big moats that we've been seeing and the whole financial industry is adopting at the moment is stablecoin and payments through blockchain. And this is a big strength of blockchains in general. The second component is decentralized data stores. And data in this scenario are blobs of data where you can basically use a decentralized network as a place for your database. Think database backing applications, but in a decentralized way. And then the third part is a computation framework that happens on the client side. When I say client here, I mean your browser or your phone, but it also means a server somewhere where it runs the computation on your behalf. And in a way that still maintains the integrity on the blockchain side. So these are like the 3 main components. What does basically make ZDA is great, giving like all of these powers together. I really believe that they bring more than the sum of like everything separately. One of the biggest unlocks with ZDAs is you get privacy by default. Privacy here doesn't mean that just your data is private and no one else can see it, but it means that you practically own your data. You own your data not just within the sphere of a specific application, but you own your data across all of the applications that you're using. Keys live with you, and you can, in a permissionless way, give companies or applications specific, fine granular access to use your data in the way that you allow them to. And every access is audited. One of the things that is very common in Web2 industry today is having end-to-end encryption or having some sort of an encryption where you give third parties access to your data, and you have to, one, trust that they are not using your data, or two, give them loose access to the data, and basically you're using a functionality, but then they have a much wider scope of like basically running computation on top of your data. With ZDAs, you can have a very fine-tuned access control to your data, but you also have that access audited at all time. If any application or any party is touching on your application, you can, one, know that in a way that's completely verifiable, and you can always revoke the access, and it acts as like an audit trail. The second part is, even though we're pushing most of the computation off-chain, you're still getting the maximum utility of building decentralized application. Your application is still have the same permissionless, trustless properties of a blockchain, if a blockchain solidity or a dApp, without having to live on-chain. Take an example of like building a collaborative note-taking application. Most of the computation that goes towards authoring the documents, authoring the notes, collaborating with other peers on those notes, cursor positions, all of the small features, they don't need to touch on the blockchain. The blockchain is there to, one, guarantee identities, guarantee payments, and coordinating the actions of writing to the decentralized data source. Coordination here means within a network, imagine if everyone here in the room is on the same document, which is a very common practice if you're in a large corporation. Only one of us will need to touch the blockchain to actually write the document or write the updates. But at the same time, that person can't be malicious because of the blockchain guarantees. And there's blockchain guarantees in place that make sure that that person can be malicious in writing something that's not the result of the computation that happened off-chain. It comes with practically limitless interoperability. Building ZDAs within the standardized form of ZDAs, where an article is an article, a media form, like whether it's an image or a music, is in its own standardized form, mean that users can freely and permissionlessly move their data around all of the applications without having to do any manual migration. This changes the game in two main ways. The first one is it kind of eliminates the cold start problems for builders. Instead of being a builder who are kind of like you need to build toward migration path or building toward getting users on your platform, you just need to build the right thing, build the features that appeal to users, and from day one, users can onboard all of their preferences, all of their data to you. Imagine if someone is building the better music streaming platform or the better note-taking application. I love Obsidian, for example, but I'm way too invested in Notion that it's very, very hard for me to do the migration to Obsidian. Imagine a world where Obsidian comes up with the best features around the same standards, and from day one, because I like it, my data is immediately available there. Not only that, but I can also, on the same note, block access from my Notion alternative. And again, this is a good utility for users, but for builders, it fundamentally changes the game of what it means to be building an application in a blockchain or a decentralized manner. Because instead of having to worry about users onboarding on your application and bringing their data, you just need to focus on building the right thing. All of this doesn't come with trade-offs. Obviously, where you're moving the computation off the chain, and you're moving the computation in a network that's one, decentralized and peer-to-peer, but two, relies on consumer hardware. You relies on your PC and your laptop and your computer. So there always are risks for this, whether it's like Byzantine peers, where imagine in an org, someone can corrupt data intentionally and try to submit that corrupted data on-chain or on the decentralized data store. Eclipse attacks, where someone would just prevent a specific person from publishing their updates. Or maybe the most challenging one is custody, which is always a problem in crypto. Because you own your keys and you own your data, that key is everything. And losing that key means losing access to your data. All of these are problems that we have solutions for. There is solutions in the wild, but we already have made a meaningful progress towards. But they basically come with a package when you try to detach computation of the blockchain. So we believe that ZDAs or hybrid executions in general are going to be a very big trend in the next couple of years. If you love this and you want to discuss it more, feel free to reach out, and I'm happy to have a discussion on this. Thank you so much.